Hey everyone, this is Dr. Calkins. We're now on experiment 15, page 97. This is definitely going to hit a lot of practice for balancing, recognizing reactions. And we'll first just give you a refresher on those reactions that we covered in the other video. One of the reactions we're looking for is the one that only has one product, called combination. We call it marriage because it's like two elements are getting together to make a compound. The reverse of that is decomposition. You have this compound, but then it breaks apart. Usually that takes a little motivation, like heat or a Bunsen burner, to get that to happen, because they're already kind of noble gas like over here and they're not over there. But definitely this is the only one with one reactant, so look for that to determine who's who. Up here, one product, down here, one reactant. Doesn't matter really the other sides. As we move down a little further, we see single replacement. Single replacement is when somebody's by themselves before and after, but that married couple is changing. So it's kind of like home wrecking or cheating or whatever. But what's most important is you're by yourself here and somebody else is by themselves over there. That requires the activity series in a later chapter, but for now we're just recognizing that somebody's a single here, somebody's a single there. Only one partner or compound before and after, that's single replacement. Double replacement. In double replacement we have two compounds, so it's like two married couples, cross charges or whatever, and then now we have two different compounds, cross different charges, but in this case we stayed ions the entire time. We didn't do electron transfer that the other ones tend to do, and we'll deal with that in a later chapter. But most importantly, 2 and 2. Both compounds, both different compounds. That's that partner swap, wife swap TV show kind of idea that we mentioned before. And then lastly, we have just burning stuff up. Just like in your car, going down the road, this organic molecule could be octane. But what's unique and useful for these is O2, CO2, and water never change. If you see those three in that order, and again, oxygen could be over here, could be first, second, doesn't matter, but you see those three, oxygen in front of the arrow, CO2 and water after the arrow, you know it has to be combustion. It doesn't have one product or one reactant. One didn't change, they both still look like compounds over here, so watch out for that kind of three trifecta for combustion. Also remember that there are things that are diatomic, especially our halogens, oxygen, nitrogen, hydrogen. Some that we didn't talk about, and they're not used too much in our class, but phosphorus is a P4, sulfur is an S8. Those are pretty rare in Intro Chem, and Gen Chem you might see those a little bit more, maybe in some of the extra credit we do. We're going to do some practice together on the next page, and then we'll get to lab. So notice here, we have balancing equations. As we balance equations, we need to remember that the same amount of mass needs to be on both sides. That's law of conservation of mass. So notice here we have 2 hydrogens, 2 fluorines, only one of each, so we put a big 2 in that kind of position. So we never change the subscript. That's determined by either Lewis dot structure connections or by charges. You can't change the charge. But what you can change is how many of each. Just remember that they're in a group together, that would multiply across. And the only way to really get good at that is to practice, and that's what we're about to do. So here's some practice. I'm going to do 1 or 2, and then let you try several more. Alright, so as we look at this example here, we're going to see that we have aluminum by itself. Oxygen doesn't have a partner, so that's still considered by itself. And then they join together. Joining together is what we call combination. So it had one product, and here was our one product. Now what we're after is we need the same number of aluminums on both sides. So if we have 1 on this side, great, but if we have 2 on this side, that's a mismatch. Law of conservation of mass says we need 2 on both sides, so if there's 2 here, we're going to need a 2 there. And so far that's looking pretty good, but as soon as we realize that, hey, this is a 2 and this is a 3, we already made a mistake. And if you're writing in pen, you're not going to be happy. And I'm writing in Sharpie, so I'm not going to be happy. So 2 and 3 only have one number in common that's going to be useful for us, and that's a 6. So if we make this a 6, 3 times the 2, so that's our 6 that we need for oxygen. This is going to be 2 times a 3, which is 6 for oxygen, which is what we want, those to match. But now we have 2 times 2, which is 4 aluminums. We only have 2, so I'm going to cheat and draw this as a 4. Problem solved. But sometimes you're going to have to erase and go back and forth. This little bounce back and forth idea is to make sure that if we start with 4, we end with 4. If we start with 6, we end with 6. And now that's a balanced equation. So there's plenty of practice on this page. And we did have that video earlier as well as the homework to help you out. So we're going to take a break and get lab set up and see you in a few minutes. So remember, as we move on to page 99, we're looking at chemical reactions, and remember there's lots of ways to recognize them. Bubbles is an easy one. That's what we're going to focus on in our lab today. We did have those in soluble solids. We'll kind of venture back with both heat and light on those with some pictures at the end of this lab. But our first lab is going to be taking hydrochloric acid, taking zinc metal, and then notice these are married up in a compound. Zinc's by himself. And if you're more active than hydrogen on that activity series we mentioned earlier on a different video, you'll notice that they traded places and hydrogen got kicked to the curb. So help recognize that and then balance it on your own. All right, so we have this lab about set up. We have our hydrochloric acid, we have our zinc, and then over here we have our lighter and our wood splint. We're going to test the kind of bubbles that we're going to make. We have 3 options. We can make hydrogen gas, which is explosive. We can make oxygen gas that makes fire even bigger. We can have carbon dioxide that would put the gas out. So what we're going to do first is add a little hydrochloric acid. And about a half a peg or so of hydrochloric acid. So there we go, it's pretty close. And then what's going to happen next is we're going to throw some zinc. Ours is a little bit old, so I'm going to throw a couple pieces in there. We're going to take this zinc. They want you to observe the appearance before, but it's kind of just a grayish silvery metal. Next, you're going to want to observe the reaction that takes place as we drop it in. Zinc is a little slower to react, especially than calcium. We'll see why as we look at the activity series. And zinc is quite a bit lower. But notice it is bubbling, so it is forming a gas. In our lab book it says hydrogen gas. We're just going to prove it. I'm going to go ahead and add another piece in there, and we'll come back in a few minutes when a significant amount of gas is formed in the tube. So notice now that we've gotten through the zinc oxide coating, it's really going to town. We're going to let it go just a little bit longer and then test it with a burning splint. So it's been bubbling a while, so we're going to go ahead and test it by lighting our wood splint. Once it has a flame, this is called a flame test. This is going to be what we're looking for the flame test result. We'll look at the zinc chloride solution appearance after the reaction's completed, and then we'll also test the touch tube for any kind of heat. All right, so round 2, we got to put another piece of magnesium, or at least in this case zinc in there, to make sure that we get the desired effect that we want. Notice that chirp noise. That chirp noise is hydrogen gas being formed. Makes that little mini explosion that we're looking for. So this is actually called a chirp test. Anytime you produce hydrogen gas, it will make that chirp in some fashion. The only reason it didn't before is because we let it wait a little too long and some oxygen and carbon dioxide probably settled in there because hydrogen's so much lighter. So go ahead and finish this portion of the lab page. If I were to touch this test tube, very, very hot. We'll come back once it's completed and check out its zinc chloride solution appearance. All right, after a few minutes, notice zinc gone and back to a zinc chloride solution, which is water soluble. And that finishes this one. We're going to move on to the next one. All right, so here on this one we have gas formation. We're looking for oxygen gas instead of hydrogen. We're going to take hydrogen peroxide, give it a little catalyst, in this case yeast, and then have it break apart. So notice as you balance it, bounce back and forth, make sure H's and O's are the same number. More importantly for this one, notice we only have one reactant. One reactant and yet now 2 products should give away what kind of reaction it is. Next thing we're going to do is look at some of our observations. So go ahead and take a minute, balance your equation, recognize the reaction, and we'll come back. All right, so we have our lab set up. First thing we want to do is look at the appearance of our peroxide. Starting to decompose a little bit, proves a little oxygen gas there maybe, but it looks like water. Observation of the reaction means we're going to have the secondary container because it's going to contain our mess. We're going to put our peroxide in first. 3% from the store. Let that sit and wait. We have active yeast from the store. It'd be tough to find that right now with everything going on in the world, but we have some in our storage. And then notice here what's going to happen with the observation of the reaction. We're going to try to get most of this air out first, so that only what we make is what's inside the bag, and here goes. I'm going to zip the bag shut a little bit. If we were to close it, it would make a bomb, and that's not what we want. So while that goes to town, notice bubbles everywhere. One of the things they're asking for is the reaction temperature, much like zinc chloride solution got very hot. This one also very warm to touch underneath. You can actually see the steam coming off of it, it's so hot. And this one's also going to be a splint test, but what's unique about this test, different from the last one, is with zinc we had the fire and we tested the air that was above it. Here we're going to blow it out. We're going to get an ember growing, nice and yellow on the end. And notice when we do this, relights. When we do this for every bubble, relights. Relights, 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 relights. And each one of those containing oxygen is what we want. So to finish this one, we just need glowing ember result, but notice again every time we tried it, relit those bubbles. All right, so in part C, we're looking for carbon dioxide. It shows up in our chemical equation that we need to balance. A little bit trickier here, so take your time balancing that one. Do recognize that some of the oxygens change, but not all of them. This acetate is part of acetic acid, so that'll help a little bit. This is a hybrid reaction. It's using an acid and a base, in this case acetic acid and sodium bicarbonate or sodium hydrogen carbonate. So it is a hybrid type, so we went ahead and gave you that answer. So go ahead and spend a little time trying to balance that one. So I have this lab set up with some baking soda. Got some of that in the cup already to go in. And here's our Ziploc bag, our secondary container in case we make a mess like the last one. Here we have some vinegar from the store, and we already have that in a flask. So we're going to do the same thing we did earlier. We're going to put the acetic acid, the vinegar solution, into the bag, much like we did with hydrogen peroxide. And if you ever had a middle school teacher do your little volcanoes, this is exactly what we're trying to recreate. We're going to try to get most of that air out of there before we add our baking soda, and then notice the reaction that ensues after. So notice there, same kind of issue, lots of bubbles. So we need to test those bubbles to make sure they're not carbon dioxide and not oxygen, not hydrogen. We need to make sure we know the difference. So with this one, we're going to use the flame just like we did for hydrogen and see what kind of molecules we made gas-wise inside. And as soon as we take it inside, it goes out. We made a baby fire extinguisher. Carbon dioxide, very common in fire extinguishers, and that's what we did here. Again, the original appearance of the solution was clear. The observation of the reactions, definitely lots of bubbles. Temperature-wise, when you feel this bag, actually very cold. And the flame test, in this case, it went out. So we're going to have a little bit of work on the next page, but that does it for the lab part. Yep. All right, in part D, we're not going to repeat this, toxic lead and so forth, to deal with our waste container, but this is the reaction that we did at the beginning of the semester. We're just revisiting it to now balance it. Notice lead nitrate had a partner, potassium had a partner with dichromate, and then both partners switched. One thing that's important about these kinds of reactions is lead is positive, potassium's positive, and notice they're not together. Nitrate's negative, dichromate's negative too, and in that situation also they're not together. So it's the positives that are changing negative partners. So take a minute to balance it, recognize that reaction, and then down here, very similar, we did this in the beginning of this semester as well. We took magnesium, lit it with a Bunsen burner, and got magnesium oxide. Notice magnesium was by itself elemental, oxygen by itself elemental, but now we have this one product. It's kind of like they got married. So balance it and recognize it, and we'll move on to the next page for a little bit more practice. All right, to wrap up this lab, we're going to work through these questions. What I'm going to do for you is save you a lot of time by not looking all these things up, because I'm sure you've forgotten most of this, given the last 3 chapters have nothing to do with reactions at all. So it's going to take us back to exam 2, and also the syllabus. The syllabus said that we would teach you a new language. That's my scare tactic at the beginning of the semester. Learning a new language is tough, especially when you're forced to do it at home, like now, or even if it were in a 16-week or 8-week or whatever kind of class. Still learning a new language is tough in that amount of time. So we're about to become bilingual because we're going to translate this English into chemistry. So as we look at this first reaction, it says nitrous oxide gas, also called dinitrogen monoxide, and water are produced. So there's our verb when ammonium nitrate is heated. So that means ammonium NH4, it's got a positive 1 charge. Nitrate, NO3, got a negative 1 charge. That's a reactant. Those charges are the same, so those are squished together, and they produce dinitrogen monoxide, so N2O, and water, H2O. Notice these charges cancel. So we're going to have to balance this one, but you'll have that fun, not me. Just remember, you have to keep these together. Whatever number you use, it'll apply for both, just like over here, and just like over here. So balancing equations is not like balancing bricks. You have 1 brick, and you have 2 bricks. You have to make sure both sides have an even amount of weight, regardless of the size of those bricks when you're done. You also need to recognize the reaction. Notice this one starts with only 1 reactant. Down here, we're going to read this one. It says iron metal disappears, so we're going to say Fe is iron. Disappears when placed in a 10 chloride solution. This is 10-2, so 10 with a positive 2 matched with chloride. That's a negative 1, so cross the 1, cross the 2. Those charges cancel. And then that's it, followed by the disappearance of 10. So the only way for 10 to disappear, or in this case up here, iron disappear, is for them to switch. So we're just going to switch these. And we're going to assume that if 10 appears, it's by itself, which it should be. And if iron is there, we're just going to pretend that it's going to have a perfect swap with a +2 iron. Although if it could happen with +3, we're not going to pretend that doesn't happen. And there you go. So again, put blanks in front, balance it, recognize it. Notice though iron and tin by themselves in that reaction. Down here it says hydrobromic acid, that's HBr. We said myride has hydraulics before, so that helps you with hydrogen bromide. Reacts with aqueous barium hydroxide. So just like this was a +1, -1, this is going to be a +2 barium and a hydroxide, which is a -1, cross the 1, cross the 2. A little bit messy there. They get parentheses 2. They form water, H2O. I'm going to go ahead and write this HOH, and I'll show you why. And then barium and bromide. So barium again, a +2, bromide, a -1, cross the 2, cross the 1. Water again, H2O, but I wrote it this way for a reason, because notice this partnership switched. So later, next week specifically, we're going to see that acids and bases make water. So since they're both switching in this case, trying to give away the answer, but the H is here and the OH is here. So just put blanks in front, balance them. But when you balance it that way for neutralization reactions of this type, which are one of our 5 from earlier, it'll be a little easier to give you a head start. As we move on to number 4, they give us propyne. Hopefully remember that prop, like a propeller, has 3 carbons. Yne is a triple bond. So here we have C3H4 given. Burns with oxygen, just remember oxygen's O2. Produces is the verb, so that's the arrow. Carbon dioxide, so CO2 and then water. Anytime you have O2, CO2, and water, that should give away what kind of reaction this is. Go ahead and balance it as well. Number 5, we have potassium chromate. Potassium is a K+, chromate, a CrO4, -2, cross the 2, cross the 1. Mixed with aluminum nitrate, so aluminum, group 13 plus 3, nitrate, T43 ion, -1, cross the 1, cross the 3, so parentheses. They produce potassium nitrate, which is a perfect match, K+ and NO3 negative, perfect match there, and we get aluminum chromate. Chromate still a -2, aluminum still a +3, so here we get a little messy and cross a 2 and a 3 on that. So go ahead and put blanks in if that helps to balance. I would probably start over here with the biggest and scariest because it's going to give you the least amount of erasing. Definitely 2 compounds, 2 compounds, 2 new compounds can help with that one. Calcium metal, Ca, no charge because it's just the element. Phosphorus, though, is P4. That's the unique one, just like S8 and all those diatomics. And then they combine. So we saw this in our first exam. If calcium and phosphorus, we would have had X's and Y's there. That's a +2 and a -3, so cross the 3, cross the 2. Calcium phosphide. Go ahead and put blanks in, but notice with this one, only one product. That should help you understand which one. Next, with number 7, we have chlorine gas. Just remember that's diatomic, Cl2. Mixed with sodium bromide, that's a perfect match with +1 sodium and bromide -1. They form salt, which is a fancy name for sodium chloride, +1 -1 still. But then when chlorine is switched, we get bromine by itself. But remember, bromine is diatomic. So go ahead and put blanks there. And balance that one. Even though chlorine does have 2 atoms, it is by itself, bachelorette, so is bromine, so it gives that one away. And then lastly, we'll see this reaction in week 12 in a little more detail. Water is H2O. Produces is the verb, so that's the arrow. Hydrogen gas, that's a H2, and oxygen is an O2. And then we put in the blanks. So balancing equations is great for the students that have done it before. It's going to be tough for those that have never done it, or maybe decades ago have done it. But what's most important to realize is when you do this in the homework in Intro Chem, they're going to give you choices. And even if you can't do this easily in these fill-in-the-blank kinds of scenarios, when you have choices, you can plug in their numbers, know which one's going to multiply correctly and which ones aren't. So it's going to be a whole lot nicer in that version of the homework and the exam. So lots of practice, and we're going to need it as we get closer to exam 4.